On March 17, 1943, over the Owen Stanley Range in New Guinea, Captain William Hargrove's P-47D Thunderbolt suffered catastrophic turbine failure at 14,000 feet. The engine, rated for 2,000 horsepower, expelled flame from exhaust ports designed to withstand 200 degrees Fahrenheit. Records from the 5th Air Force showed turbine blade failures accounted for 23% of mechanical losses that quarter. Hargrove's aircraft descended in a controlled glide, the Pratt & Whitney R2800 engine silent except for windmilling propeller noise. Ground crews at Port Moresby recovered the aircraft intact. What they found inside the cowling contradicted every metallurgical assumption. 3 turbine blades, subjected to temperatures exceeding operational limits, showed minimal thermal degradation. The maintenance log, signed by Staff Sergeant George Pemberton, noted simply, "Blades intact, composition unknown." In Berlin, within 6 weeks, a similar discovery would occur under entirely different circumstances, setting parallel investigations in motion across 2 continents. By late March 1943, German metallurgical research had intensified under Reich's Luftfahrtministerium Directive RLM 203, prioritizing engine durability for extended combat operations. At the Kaiser Wilhelm Institute's satellite facility outside Berlin, Dr. Wilhelm Hartmann examined turbine components recovered from a downed American P-47 near Schweinfurt on February 24th. The blade section, catalogued as specimen US 47009, measured 4.2 inches in length and retained structural integrity despite visible fire damage. Hartmann, who had published 12 papers on high-temperature alloys before the war, recognized immediately that standard chromium steel compositions could not explain this resilience. The testing chamber, installed in January under emergency industrial orders, reached 1400 degrees Celsius. Hartmann's assistant, Klaus Reinhardt, a chemistry doctorate from Heidelberg, positioned the blade fragment inside quartz housing. As the furnace ignited, both men watched through protective glass. Expected metal fatigue did not occur. At 1350 degrees, the alloy maintained cohesion. Hartmann recorded in his laboratory notebook, "Thermal resistance exceeds known parameters by factor of 1.7. The composition analysis revealed nickel content at 18.3%, chromium at 14.1%, with trace cobalt and manganese. These ratios defied conventional metallurgy doctrine published in every technical manual Hartmann had studied. The implications registered slowly. If this alloy could be synthesized, German aircraft engines might sustain combat stress, currently causing 31% of Luftwaffe mechanical failures, according to January's operational summaries. Hartmann drafted a priority memorandum to the Reich Air Ministry, stamped it urgent, and handed it to Reinhardt for immediate courier dispatch. The document, recovered in Allied archives after the war, contained one underlined sentence: "Replication, essential for operational parity." Outside the laboratory window, Berlin's factory district continued round-the-clock production, unaware that a fragment of American engineering had just redefined the boundaries of possibility. Captain Hargrove's P-47D remained grounded at Port Moresby for 11 days, while maintenance crews assessed turbine damage. Staff Sergeant Pemberton, a pre-war mechanic from Ohio with 14 years of aircraft experience, supervised the engine teardown on March 19th. The R2800 double Wasp engine, serial number 428066, had logged 247 combat hours since installation. Pemberton expected complete blade disintegration based on observed flame temperature and engine failure protocols outlined in Technical Order 0245 AA2. Instead, visual inspection revealed 3 of 18 turbine blades showed only surface oxidation. The remaining 15 exhibited standard wear patterns consistent with normal operation. Pemberton filed his report with the 5th Air Force Engineering Section, noting discrepancies between expected and observed damage. The document, archived at Maxwell Air Force Base, included hand-drawn diagrams showing blade cross-sections and heat distribution patterns. His summary stated, "Metallurgical composition warrants laboratory analysis. Durability exceeds specifications." The report reached Wright Field, Ohio, by military courier on April 2nd, where metallurgist Dr. Robert Evans initiated formal investigation under Project MX-138, a materials research program tracking combat performance anomalies. Meanwhile, Hargrove returned to flight status on March 30th with a replacement engine. The squadron, assigned bomber escort duty over Leh, operated at maximum tempo, 4 sorties weekly per pilot. Loss rates for P-47 units averaged 8.4% monthly, split between combat and mechanical causes. Hargrove's survival reinforced growing recognition among pilots that engine reliability mattered as much as enemy action. In the ready room, conversations shifted from tactics to turbine performance, a subtle evolution reflecting hard-won operational knowledge. By month's end, Wright Field had logged 14 similar turbine anomalies from Pacific and European theatres. Dr. Evans, reviewing metallurgical data, found consistency across all samples. Elevated nickel-chromium ratios beyond standard specifications. His April 15th memo to Army Air Forces Materiel Command recommended immediate alloy refinement for next-generation engines. The race to understand and replicate this material had begun in earnest, though neither American nor German researchers yet knew they pursued identical goals. Dr. Hartmann's team worked through April under conditions that reflected Germany's deteriorating industrial capacity. The Kaiser Wilhelm facility operated with reduced electrical allocations, limiting furnace time to 6 hours daily. Allied bombing of the Ruhr Valley had reduced nickel imports by 40% since January, forcing careful rationing of experimental materials. Despite constraints, Hartmann proceeded methodically. On April 8th, his team attempted their first synthesis using refined nickel from Norwegian sources and chromium from Turkish suppliers. The initial batch, designated alloy K1, failed at 1200 degrees Celsius, fracturing along grain boundaries that indicated improper crystalline formation. Reinhardt proposed altering the cooling sequence based on research into Japanese sword-making techniques that controlled metal microstructure through temperature gradients. The second attempt, on April 14th, incorporated staged cooling, rapid descent to 900 degrees, then gradual reduction over 40 minutes. This batch, alloy K2, withstood 1280 degrees without structural failure. Hartmann's notebook entry read, "Cooling rate determines grain alignment. Thermal shock resistance achieved." The breakthrough confirmed that manufacturing process mattered as much as chemical composition. Testing protocols expanded to include thermal cycling, simulating repeated engine starts and shutdowns. Over 5 days, alloy K2 endured 87 cycles between ambient temperature and 1350 degrees, showing minimal degradation. Hartmann calculated that conventional turbine steel failed after 12 cycles under identical conditions. This 7-fold improvement represented a fundamental materials advancement, one that could extend engine operational life from 150 hours to potentially 800 hours between overhauls. The economic and strategic implications were immense. Fewer replacement engines, reduced production demands, and improved aircraft availability rates. On April 22nd, Hartmann submitted his findings to Oberkommando der Luftwaffe through official channels. His report, classified Geheime Kommandosache, outlined replication procedures and recommended immediate production trials. The document noted, "Alloy composition permits sustained high-temperature operation exceeding current limits by minimum 200 degrees Celsius." Within the bureaucracy of wartime Germany, this report would circulate for 6 weeks before reaching decision-makers with authority to implement changes. Time, as always, in war, remained the critical variable neither side could manufacture. By May 1943, pressure mounted within German Military Aviation Command to address escalating engine failure rates. Colonel Ernst Schmidt, assigned to Luftwaffe technical operations at Rechlin-Laerts proving grounds, reviewed monthly loss statistics showing 147 aircraft grounded for engine repairs across fighter wings in April alone. These figures, compiled from unit reports throughout occupied Europe, indicated systemic problems that tactical adjustments could not solve. Schmidt, a career officer who had commanded bomber squadrons over Poland in 1939, understood that mechanical reliability determined operational tempo as much as pilot skill or aircraft numbers. On May 3rd, Schmidt convened a technical conference at Rechlin, bringing together engineers, metallurgists and field commanders. Dr. Hartmann presented alloy K2 results, demonstrating blade samples that had survived extreme testing. The audience, 26 officers and 7 civilian specialists, examined physical evidence and reviewed thermal cycling data. Schmidt asked direct questions about production feasibility, timeline, and material requirements. Hartmann's response, recorded in conference minutes, acknowledged challenges. Full implementation requires 8 to 12 months, dependent on nickel availability and tooling modifications. Schmidt faced a classic wartime dilemma: invest resources in unproven technology or accept current loss rates. The Luftwaffe was simultaneously developing the Messerschmitt Me-262 jet fighter, which consumed enormous quantities of scarce materials including chromium and cobalt. Allocating additional resources to turbine alloy research meant diverting them from other critical programs. Yet continued engine failures reduced effective strength without any combat engagement. The calculus was brutal and clear. After 2 days of deliberation, Schmidt authorized limited production trials at the Junkers engine facility in Dessau. His directive, dated May 6th, allocated sufficient nickel for 50 prototype turbine blade sets to be manufactured and tested under operational conditions by August. The order included provisions for metallurgical oversight and mandatory failure analysis. Schmidt's covering memo stated, "Operational necessity justifies experimental risk." This decision, made under pressure and with incomplete information, would influence German aviation capabilities through the war's final years. Across the Atlantic, parallel decisions were taking shape under different constraints but similar urgency. At Wright Field, Dr. Robert Evans faced different challenges analyzing American turbine anomalies. His laboratory, established in 1941 under the Army Air Forces Materiel Command, possessed superior equipment and unrestricted material access compared to German facilities. By mid-May, Evans had examined 23 blade samples from combat-damaged engines, all showing unusual durability. Spectroscopic analysis revealed consistent nickel-chromium ratios ranging from 17.8 to 19.2% nickel and 13.5 to 14.7% chromium. These values suggested that current Pratt & Whitney and Allison manufacturing processes occasionally produced superior alloys through random variation in source material composition. Evans hypothesized that tighter composition controls could reliably replicate the superior performance. On May 18th, he initiated collaboration with Republic Aviation Corporation, manufacturer of the P-47, to review their turbine blade supply chain. The investigation traced materials to three primary steel foundries: Pittsburgh, Cleveland, and Gary. Each foundry used slightly different nickel sources and refining techniques, creating composition variations of 2 to 3%. This variance, normally considered acceptable, apparently crossed a critical threshold where mechanical properties changed dramatically. Working with Republic's chief metallurgist, Thomas Brennan, Evans designed experimental batches with precisely controlled nickel-chromium ratios. By June 1st, initial castings were complete and undergoing thermal testing at Wright Field. The results matched predictions: blades with 18.5% nickel and 14% chromium maintained integrity at 1,150 degrees Fahrenheit for sustained periods, while those at 16% nickel degraded rapidly. The relationship between composition and performance proved non-linear, with narrow optimal ranges producing maximum durability. Evans documented findings in a technical report distributed to engine manufacturers on June 9th. His conclusion recommended standardizing alloy composition at the upper end of currently acceptable ranges, a modification requiring minimal retooling but promising significant performance gains. The report estimated that implementation across all production lines would take 4 to 6 months, with first operational engines available by November 1943. This timeline, though aggressive, reflected America's industrial capacity advantages: coordination between military research, private manufacturers, and multiple supply chains operating at full capacity. Meanwhile, Pemberton at Port Moresby continued routine maintenance, unaware that his March report had triggered this investigation. He noticed newer engines seemed more robust, though official explanations remained classified. In the maintenance logs, he simply noted fewer turbine failures per flight hour, the metric that mattered most. Summer 1943 brought intensified operations across all theatres. In New Guinea, the 5th Air Force supported Allied advances along the coast, with P-47 units flying interdiction missions against Japanese supply lines. Hargrove's squadron logged increased sortie rates, 32 missions in June alone, averaging 4 hours each. Engine reliability became paramount as distance from maintenance facilities stretched logistics to limits. A mechanical failure over enemy territory meant either emergency landing in hostile jungle or ditching in the Coral Sea, with survival odds poor in both scenarios. On June 24th, during a bomber escort mission to Rabaul, Hargrove's flight encountered Japanese fighters at 22,000 feet. The engagement lasted 14 minutes, during which Hargrove's engine operated at maximum continuous power, 2,300 RPM at high manifold pressure, generating thermal loads approaching design limits. Post-flight inspection revealed turbine temperatures had reached 1,380 degrees Fahrenheit, exceeding normal operating parameters by 180 degrees. Yet the engine showed no degradation. Pemberton, examining the turbine assembly, found minimal blade wear and no cracking. His maintenance log entry noted, "Sustained high-temp operation, no adverse effects observed." This operational resilience, repeated across numerous aircraft, transformed pilot confidence. Aggressive tactics that previously risked mechanical failure now seemed viable. Squadron commanders adjusted doctrine accordingly, authorizing extended combat at maximum power when tactical situations demanded. The change was subtle but significant. Improved materials enabled tactical flexibility that translated to operational advantage. By July, the 5th Air Force reported 11% increase in effective sorties despite no change in aircraft numbers, a productivity gain attributable directly to reduced mechanical downtime. Back at Wright Field, Evans tracked these operational reports with professional satisfaction. His June recommendations were being implemented, with first modified engines entering service in July. Early feedback confirmed laboratory predictions. Thermal endurance had increased measurably. On July 19th, Evans received authorization to expand research into next-generation superalloys, investigating cobalt additions and alternative heat treatments. The institutional machinery of American military-industrial cooperation was functioning effectively, translating battlefield observations into laboratory research, then back to improved equipment in a continuous cycle. This iterative process, supported by ample resources and efficient communication networks, gave American aviation a cumulative advantage that would compound throughout the war. In Germany, production trials at Dessau proceeded slowly through summer. Juncker's engineers, working with Hartmann's specifications, manufactured 32 blade sets by late June. Installation began in July on BMW 801 radial engines powering Focke-Wulf FW-190 fighters. Initial results appeared promising. Engines equipped with alloy K2 blades completed operational tests without thermal failures. However, implementation faced obstacles beyond technical challenges. Allied bombing intensified through July, targeting German industrial centers. On July 24th, RAF Bomber Command struck Hamburg in Operation Gomorrah, killing 42,000 civilians and destroying significant portions of the city's industrial district. While Dessau remained undamaged, the broader disruption to transportation networks delayed nickel shipments from Norway. Production schedules slipped. By August, only 18 blade sets were available for field testing, far below the 50 originally planned. Colonel Schmidt visited Dessau on August 12th to assess progress. His inspection report, preserved in Luftwaffe records, acknowledged technical success but noted procurement difficulties. Alloy performance verified under operational conditions, manufacturing constrained by material shortages and competing program demands. The Me-262 jet program, entering critical development phases, claimed priority for nickel and chromium allocations. Schmidt faced a stark choice: support incremental improvements to existing piston engines or invest in revolutionary jet technology. The decision, made at higher command levels, favored the Me-262. Dr. Hartmann received notification on August 19th that further alloy development would continue at reduced priority. His laboratory's material allocations were cut by 60%, effectively halting large-scale testing. The order, signed by General Luftzugmeister Erhard Milch, stated, "Research continuance authorized at minimal resource levels." Hartmann, reading this bureaucratic language, understood its meaning. The program had been shelved. His work would continue in theory, but lacked practical support for meaningful progress. On August 27th, Hartmann wrote to his wife, Eva, who had evacuated to Bavaria with their 2 children. The letter, surviving in family archives, revealed his frustration. The work proceeds, but resources flow elsewhere. One cannot argue with strategic priorities, yet I wonder if incremental improvements are dismissed too readily. This tension between revolutionary innovation and evolutionary refinement characterized Germany's late-war technological choices. Often, pursuit of dramatic breakthroughs meant abandoning proven improvements that might have provided more immediate operational benefits. By September 1943, improved turbine alloys were becoming standard in American engine production. Republic Aviation had fully integrated Evans's specifications into P-47 manufacturing, with similar adoption by other airframe companies. Pratt & Whitney modified procurement contracts to require tighter composition controls from steel suppliers, eliminating random variation that had previously caused inconsistent blade performance. These changes, implemented across the industry, represented American manufacturing's ability to rapidly disseminate technical improvements through coordinated supply chains. Statistical evidence of improvement appeared in maintenance records by October. The 5th Air Force reported turbine blade failures decreased from 23% of mechanical losses in the first quarter to 9% in the third quarter, despite increased operational tempo. Similar trends appeared in 8th Air Force data from European operations, where high-altitude bomber escorts placed extreme demands on engine performance. The cumulative effect was measurable. Aircraft availability rates improved by 7% between June and October, equivalent to adding dozens of aircraft to operational strength, without building a single additional plane. Hargrove, now a major after promotion in August, continued flying missions over New Guinea and later the Philippines. His logbook recorded 147 combat hours between March and November, during which he experienced 0 engine failures attributable to turbine problems. On November 3rd, during a mission over Rabaul, his flight encountered heavy anti-aircraft fire. Hargrove's aircraft took flak damage to the engine cowling, but maintained power and returned to base. Post-flight inspection found shrapnel had penetrated the cowling, but missed critical engine components. The turbine blades, however, had endured significant vibration from the unbalanced engine operation during the emergency return flight. Pemberton's inspection found no cracking or warping, resilience that might not have existed 18 months earlier. This reliability, multiplied across thousands of engines, transformed operational planning. Mission profiles extended, tactical aggression increased, maintenance intervals lengthened. These incremental advantages, invisible in any single engagement, accumulated into strategic effect. American air superiority, built on many factors, rested partly on the unglamorous foundation of metallurgical improvement, better steel enabling longer missions, faster turnarounds, and higher sortie rates. The war would be won by combined factors, but materials, science played its quiet, essential role. In early 1944, Dr. Hartmann's research continued at minimal scale. The Kaiser Wilhelm facility operated on skeleton staff, with most resources diverted to urgent production programs. Allied bombing had intensified, with Berlin subjected to regular raids by RAF Bomber Command, and, increasingly, 8th Air Force daylight attacks. On February 3rd, a raid targeting industrial districts destroyed buildings 400 meters from Hartmann's laboratory. The facility survived but lost electrical power for 11 days, halting all furnace operations. During this forced inactivity, Hartmann reviewed his accumulated data with Reinhardt. Their notebooks contained 2 years of experimental results, 347 alloy compositions tested, 892 thermal cycles documented, and detailed analysis of 15 failure modes. The research represented one of the most comprehensive metallurgical studies conducted under wartime conditions, yet it had produced limited practical impact on German aviation. The disconnect between technical achievement and operational implementation frustrated both men. On March 5th, electrical service restored, Hartmann conducted final tests on an advanced alloy variant designated K7, incorporating molybdenum additions suggested by Reinhardt's earlier research. The alloy withstood 1,180 degrees Celsius for 2 hours without degradation, exceeding all previous results. This performance, which might have revolutionized German engine capabilities, came too late. By March 1944, the Luftwaffe faced fuel shortages, pilot losses, and overwhelming Allied numerical superiority. Superior turbine blades could not overcome these fundamental deficits. Hartmann prepared a final comprehensive report, documenting all research findings and manufacturing procedures. The 127-page document, submitted April 10th, contains sufficient detail for any competent metallurgist to replicate his work. He addressed it to the Reich Air Ministry with a cover letter stating, "This research establishes foundation for post-war aviation development, regardless of current operational constraints." The letter, recovered by Allied investigators, in 1945 revealed Hartmann's recognition that his work transcended immediate military application. He was documenting knowledge for future use, whenever circumstances might permit its implementation. On April 15th, Hartmann received orders to evacuate the laboratory and relocate equipment to a facility in southern Germany. Allied forces were advancing from both east and west. Berlin's industrial capacity was collapsing. As Hartmann supervised packing of essential materials, he reflected that his research had succeeded technically but failed strategically. Timing, resources, and institutional priorities had determined outcomes as much as scientific merit. The lesson was harsh but clear. American technical intelligence operations intensified as Allied forces advanced across Europe. Teams from the Combined Intelligence Objectives Subcommittee, CIOS, identified German research facilities for investigation. The Kaiser Wilhelm Institute appeared on priority lists due to its known metallurgical work. On May 2, 1945, 3 days after Berlin's surrender, a CIOS team entered the facility. They found most equipment removed, but discovered archived documents including Hartmann's research notebooks. Dr. Lawrence Norris, a metallurgist from MIT attached to the CIOS team, examined the notebooks with growing recognition. Hartmann's work paralleled American research but included several innovations American scientists had not pursued. Norris noted particularly the molybdenum additions in alloy K7 and the staged cooling procedures Hartmann had developed. His field report stated, "German research achieved comparable results through independent methodology. Several techniques merit investigation for possible adoption." By June, Hartmann's documents were in Washington, translated and distributed to researchers at Wright Field and various corporate laboratories. Dr. Evans received copies and immediately recognized the value. On July 3rd, he initiated tests incorporating Hartmann's molybdenum ratios into experimental alloys. Results confirmed the German research. Molybdenum additions of 3 to 5% increased high-temperature strength by additional 12% beyond existing superalloys. This finding, validated through independent testing, demonstrated that parallel research under different conditions could yield complementary insights. The integration of German and American metallurgical knowledge accelerated post-war superalloy development. By 1946, a new generation of alloys incorporated best elements from both research programs. American nickel-chromium formulations combined with German cooling techniques and molybdenum additions. These advanced materials enabled jet engine development, supporting temperatures exceeding 2,000 degrees Fahrenheit required by gas turbine operation. The wartime research, conducted under urgent military necessity, provided foundation for post-war aviation revolution. Dr. Hartmann, located in July 1945 at a facility in Bavaria, was interviewed by American technical intelligence officers. He cooperated fully, explaining his research methodology and confirming details in recovered documents. His treatment reflected Allied recognition that scientific knowledge transcended wartime enmities. On August 15th, Hartmann signed a contract with the U.S. Army Air Forces to continue his research in America, joining other German scientists whose expertise was valued for future development. The knowledge, created under desperate circumstances, would serve peacetime progress. By war's end, The statistical impact of improved turbine alloys was quantifiable in American operational records. The Army Air Forces compiled comprehensive maintenance data showing turbine blade failure rates declined from 18.4 per thousand flight hours in early 1943 to 3.2 per thousand flight hours by May 1945. This improvement, achieved through standardized alloy compositions and manufacturing procedures, represented one of numerous incremental advances that collectively enhanced operational effectiveness. The human cost of engine reliability was harder to measure, but no less real. Pilots who survived mechanical failures, like Hargrove, completed their tours and returned home. Those whose engines failed at critical moments, during takeoff, in combat, or over hostile territory, often did not. The difference between survival and loss sometimes depended on whether turbine blades maintained integrity under extreme stress. Statistics captured numbers, behind each number was a human outcome. Hargrove returned to the United States in December 1945, having completed 63 combat missions. He transitioned to civilian life, using GI Bill benefits to study mechanical engineering at Ohio State University. In his graduate thesis, completed in 1949, he analyzed engine reliability factors affecting wartime operations. One chapter examined metallurgical improvements, drawing on his personal experience and official records. His conclusion noted, incremental technical refinements, though individually modest, accumulated into substantial operational advantage. Staff Sergeant Pemberton remained in the Army Air Forces, later the Independent Air Force, retiring in 1960 as a Chief Master Sergeant. His career spanned the transition from piston engines to jets, and he witnessed firsthand how wartime metallurgical research enabled post-war aviation development. In retirement interviews, he emphasized that maintenance personnel understood these connections clearly. Better materials meant fewer failures, which meant pilots came home. The abstractions of research translated directly to concrete human outcomes. Dr. Evans continued superalloy research at Wright Field through the 1940s and 1950s, contributing to jet engine development that enabled military and commercial aviation advances. His wartime work on turbine blade alloys formed the foundation for more sophisticated materials that would power supersonic flight and space exploration. The progression from 1943's improved nickel-chromium alloys to the complex superalloys of later decades illustrated how incremental advances compound over time into revolutionary capabilities. Post-war analysis placed turbine alloy development within the broader context of industrial mobilization. The United States produced 300,317 aircraft during the war, more than all other combatants combined. This numerical superiority depended on manufacturing capacity, but also on materials science that enabled reliable mass production. Standardized alloy compositions derived from wartime research allowed factories to produce consistent, high-quality engines at unprecedented scale. German aviation production reached 190,907 aircraft between 1939 and 1945, impressive given economic constraints and Allied bombing. However, production numbers alone didn't determine outcomes. Operational availability, the percentage of aircraft ready for missions, mattered as much as total production. Germany's inability to maintain high availability rates, partly due to material shortages affecting engine reliability, reduced effective air strength below nominal numbers. This factor, among many others, contributed to the Luftwaffe's decline after 1943. The metallurgical achievements of both sides demonstrated scientific capability under pressure. German researchers, despite limited resources, produced sophisticated alloys comparable to Allied work. American researchers, with superior resources and institutional support, translated discoveries into widespread operational implementation more effectively. The difference lay not in scientific merit, but in industrial capacity and resource availability. Both sides possessed technical competence. Outcomes depended on broader strategic and economic factors. By 1946, the jet age was beginning. German wartime research on turbojets, particularly the Jumo 004 and BMW 003 engines, influenced Allied post-war development despite Germany's defeat. Similarly, wartime superalloy research by both sides provided essential foundation for jet turbine blades, which faced temperatures and stresses far exceeding piston engine requirements. The knowledge created under wartime urgency found its fullest expression in peacetime application. On November 12, 1947, exactly 4 years after his November 1943 mission over Rabaul, Hargrove attended an aviation conference in Dayton, Ohio. Among the speakers was Dr. Hartman, now working for the U.S. Air Force, presenting research on next-generation superalloys for jet engines. After the presentation, the two men met briefly. Their conversation, witnessed by several colleagues, was cordial and focused on technical matters. The wartime context that had made them adversaries had transformed into post-war collaboration. The metal they had both depended upon in different ways now served common purposes. The legacy of wartime metallurgical research extended far beyond its immediate military applications. By the 1950s, superalloys enabled commercial jet aviation, with aircraft like the Boeing 707 relying on turbine blades derived from wartime materials science. The progression from Hargrove's P-47 engine to Pan Am's transatlantic jetliners spanned barely 15 years, and remarkably rapid technological evolution, enabled by continuous refinement of high-temperature alloys. In 1963, 20 years after his initial research, Dr. Hartman published a retrospective article in the Journal of Materials Science. He reflected on the parallel development of superalloys during the war, noting, "Scientific progress proceeds through convergent evolution. Similar problems generate similar solutions when competent researchers apply rigorous methodology." His article acknowledged both German and American contributions, placing them within a continuum of metallurgical advancement that predated the war and continued long after. Dr. Evans, retiring from government service in 1965, had witnessed superalloy development through multiple generations. His farewell lecture at Wright-Patterson Air Force Base surveyed the field's evolution from wartime urgency through post-war application. He emphasized that breakthrough materials emerged from systematic research rather than sudden inspiration, a process requiring institutional support, adequate resources, and sufficient time for iterative refinement. The 1943 turbine blade improvements, he noted, resulted from focused investigation of observed anomalies, science proceeding through careful observation and methodical testing. The archival record of wartime metallurgical research fills multiple linear feet at various institutions: Wright-Patterson Air Force Base, the National Archives, university collections, and corporate archives. Within these documents lie thousands of measurements, test results, and engineering drawings that documented humanity's expanding mastery of materials under extreme conditions. The numbers tell stories: temperature curves, failure rates, composition percentages, and production quantities that collectively represent applied scientific knowledge. On March 17, 1993, 50 years after his emergency landing in New Guinea, William Hargrove attended a reunion of P-47 pilots at the Air Force Museum in Dayton. At 81 years old, he walked through the museum's galleries, pausing before a restored P-47D Thunderbolt. His reflection in the polished aluminum skin showed an old man remembering his youth. He touched the engine, cowling briefly, a gesture connecting past to present. The turbine blades inside that engine, manufactured in 1944, incorporated the improved alloys developed through wartime research. They represented incremental human progress, careful observation, rigorous testing, and systematic refinement producing measurable advantage. No single discovery won the war. Victory emerged from countless improvements, compounded over time. The metal itself, forged under pressure and refined through necessity, endured as testament to human ingenuity applied under the most demanding circumstances. In the museum's archives, Pemberton's March 1943 maintenance report resided in a file alongside thousands of similar documents. The notation, "blades intact, composition unknown," had triggered investigation that connected laboratory to battlefield, theory to application, and wartime necessity to post-war progress. The file closed without ceremony. The numbers had already written their story.